All right, so lecture topic today is the energy that's stored in a capacitor. So if we look at our list of objectives, it's B.2.B5 this time. I'm circling it now. Just this one for today. Derive and apply expressions for the energy stored in a parallel plate capacitor and for the energy density in the field between the plates. So that's what we're going to figure out today. How much energy is stored in a parallel plate capacitor and what's the energy density, so the energy per unit volume in the electric field in between the plates. And as we'll see, and I want to kind of emphasize, when we think about energy that's stored in a capacitor, where is that energy? It's actually in the electric field itself, right? We know if we have a parallel plate capacitor, there's a uniform electric field in between those plates. And the energy is actually, the best way to think of it, or one of the clearest ways to think about it, is the energy is stored in the electric field itself. All right. So how much energy are we going to be storing in a capacitor? And then we'll also look at how much energy per volume there is. All right. Good. So when we're asking how much energy we store in a capacitor, it's easier to answer if we think about an identical question or an equivalent question, which is how much work does it take to charge the capacitor? Right? If you think about conservation of energy, that should make sense. It's going to take some amount of work if we have two uncharged plates. It's going to take work if we want to get a positive charge on one and a negative charge on the other, right? Because that's going to involve pulling charges that attract apart. So it's going to take work to do that. And if we can figure out how much work it takes, that'll tell us how much electrical potential energy we end up having inside the stored in the capacitor. So how do we figure out how much work there's going to be done? So if you imagine, so what I've drawn here, so we want to charge the capacitor up to some charge capital Q. So let me add to this question: how much energy is stored in a capacitor when its charge is capital Q? That's the total charge we're going to charge it up to. So if we have a couple of plates and there's already some charge, maybe this is kind of an intermediate stage, right? If there's some charge on the plate, then we can figure out the work it's going to do to move another piece of charge, of positive charge, say from the minus Q plate to the plus Q plate. We can figure out how much work that's going to take because we know the potential difference, right? We know the potential difference, and we learned this in the last lecture, between the two plates. Does anybody remember? Study that hard? What's the potential difference between two plates? What's the equation we derived last time?
The integral of, and that was just E times distance.
Okay, so that's true. Yeah, you're right. But let's say we don't know that we would need to know what the electric field in between the plates was, right? But all we know is the charge on the plates is Q. We did get a value for the potential on a charged capacitor was the Q divided by C, right? And that actually just comes, well, we didn't calculate that. That was what we defined capacitance to be, right? Capacitance is just how much charge per volt there is, right? So if you rearrange that, you can see that the voltage is just how much, where the potential difference is the charge divided by the capacitance, right? And that comes.
Capacitance.
Sorry?
But then we don't know the capacitance.
Well, that's true. But remember, if we have a capacitor and we know the area of the plates and the distance between the plates, right? We do know the capacitance of a parallel plate capacitor. Let's write that down now because we're going to need it later. What was our result from the last lecture for capacitance? Does anybody remember that? And now that's just this is true for any capacitor, right? That's the definition. But for a parallel plate capacitor, what we ended up with.
Charge density over electric field times A. I don't know.
Yeah, you're pretty close, right? Charge density over electric field could be in there, but instead of in terms of charge density, which would be this Q over the area, we also found the expression that it was just epsilon naught times the area divided by the d, the distance between the plates, which is the same as saying it's the charge density times the area divided by the electric field times d, which I think was part of our work last time. So if we know that, we can assume, I guess, that we do know the capacitance, right? Because we'll say we know the area of the plates and we know the distance between them. So it's kind of a known capacitor, but we just want to know how much work it's going to take to charge them. So we've got, we know this is the potential difference, right? How much charge there is on the capacitor divided by C. And how do we go from potential difference to energy or to work? That's a simple expression, right? That we should know. Because potential is, remember, our potential or difference, delta V, is just the potential energy per unit charge.
So we should take the derivative.
Well, we'll need to. We don't need to take the derivative of this, right? We know that. So we know that the work it's going to take to move a small bit of charge. So, right, an infinitesimally small piece of charge, dq, from one plate to the other plate. So if it's an infinitesimally small piece of charge, we're going to get an infinitesimally small piece of work. But we know that the work is just going to be the charge or the dq times the potential difference. Right. If we move and the reason we're moving little pieces, right, is because every time we move a charge, we're changing this q, right? So if we have to move through potential difference, q over c, well, once we move some charge over here, this q is going to be different now. Right, so that's why we're going to need to take an integral, right? We have a little piece of work is going to be a little piece of charge times the potential difference, right? Because work is just charge times potential difference, or energy is just charge times potential difference. So we can also see then that using what we have here, that little piece of work is going to be the little piece of charge that we need to move times whatever charge is currently on the plate divided by the capacitance. So to move a small piece of charge, and I'm sorry, I'm kind of belaboring the point, but to move the small piece of charge, the work we do to move a small piece of charge is that small piece of charge times the charge on the plate divided by C. Are we okay so far with this? Because now that we know how much work it takes to move one piece of charge, we can figure out the total work it's going to take. Right? The total work to move all that charge Q is going to be the sum of each little piece of work to move a little piece of charge. And when we're talking about infinitesimally small pieces of charge or pieces of work, we make that sum into an integral. So the total work we're looking for is just the integral of dW, right? The sum of each little piece of work it takes to move each little piece of charge from one plate to the other, right? And it has to be an integral because every time we move a piece of charge, now the charge on the plate is different, and we have a different potential difference, so it's going to take a different amount of work, more actually, to move that next piece of charge. All right. So now we need to do the integral, right? But we already found what dW is, right? That's this dq times q over c. So all right, this is, and we need limits as well, right? And since I've converted from work to charge as my variable of integration, my limits are going to be the starting and ending amounts of charge on the plates, right? And if I'm going to charge the plate up, that means I'm starting really at 0 and ending with my total charge, capital Q. That's how much work it's going to take to charge the plate up completely. Right? And it helps to, and it's always good to think about what we're doing and why, right? And you can kind of see at the beginning when these plates are completely uncharged, right? Q has a value of 0, and then it doesn't take any work, right? The first little piece of charge it takes to move from one plate to another takes no work because the plates are uncharged, right? So there's no resistance to moving a positive charge from one plate to the other. Of course, as Q increases, right, then the charge increases, so it takes more work to do that. So now we can do the integral, and I hope you can do this integral, right? If we're integrating Q dq, right, capacitance is a constant. What's the integral of just Q dq? Or x dx, if it helps you to think of it like that.
Wouldn't it just be d?
Not d, right? Because dq is the variable of integration, right? So if I'm integrating, well, c is a constant, right? So let's pull that out, and then we just have this integral. I don't think anybody would have a problem doing it if this integral was just integral x dx, right? And I know there's some, I'm not sure how far, has those of you in AB, Calc AB, gotten to integrals yet?
No.
Oh, still, oh man. All right.
No, we're doing like L'Hopital's and like the first derivative test and such.
Right. Yeah, I mean, and that's all great too, but got to, okay, so fair enough. Hopefully, yeah, I guess, when do they usually, is it, I thought it was usually first semester, but maybe it's not that they get there. Okay, anyway, remember when we do integrals, it's the antiderivative, right? So if we want to do, basically we want a function whose derivative is q, right? If we're taking the antiderivative, then we need the function whose derivative is q, right? What function would have a derivative of q?
Q squared.
Squared, almost, yeah. Because the derivative of q squared is 2q.
Half Q squared.
Yeah, half 2. Yeah, that's good, you're right. So what we get is 1 over c, and then we have times q squared over 2, and then we evaluate at our limits 0 and capital Q. Right, when we plug in the 0, q squared is just 0. So what we end up with when we plug in capital Q is just, whoops, I forgot the 2 there again. Oh, but I put an extra c, I'm sorry. So what we get when we do this integral is capital Q squared over 2c. All right, so that would be the amount of work it takes to charge up a capacitor. So that's the energy in the capacitor.
I remember the integration a little bit from physics.
Yeah,
but when you use like Q and other variables, I just get lost.
Yeah, so right, when you took mechanics, it's there's some integration, but mostly just position, velocity, and
just for T, yeah.
Right, integrating over time. So I mean, the math isn't any different when you're integrating over charge instead of over time. It's maybe a little harder to picture what's going on and why you're doing it. But if you would integrate the integral of t dt, right, you would get t squared over 2. So yeah, I know the yeah, and maybe I'll have to put together something like a what you need to know as far as integration, just for this test, because I'll try to put something together like a big integral review kind of a thing, or review for some people, new for others. But okay, and we'll have to come back to that. But let's keep going for now. That's all the calculus we need to do for this lecture today. Now that we found the work done to charge up this parallel plate capacitor. And remember, the work done, that's just going to be the amount of electrical potential energy that's in there. And just moving a little quicker, right? We see that it's 1/2 Q squared over C. There's a couple of other ways we can write this. If we remember this definition of capacitance, that the capacitance is this charge divided by the potential. Sometimes if we have a charged up capacitor in front of us, it's not very easy to measure how much charge is on the capacitor directly. We'll usually know the capacitance of a capacitor. The manufacturer will mark it on the capacitor, but it's a lot harder. It's a lot easier to measure the voltage, the potential difference between the plates, than it is to actually measure the charge. So a lot of times we'll replace Q with C times V. So really, this is also going to be equal to, if I replace Q with capacitance times potential difference here, I get C times V all squared over 2C, which gives me C times potential difference squared over 2. So another way to write the energy inside a capacitor is 1/2 capacitance times potential squared. Which is probably the most useful way to write that energy. And just to be complete, we could also write it in terms of just Q and V and not capacitance. And if we did that, I won't do it out, but we would get 1/2 Q times delta V. All right, so these are all equivalent expressions for the energy stored in a capacitor. And this, by the way, this is energy stored in any capacitor, not just parallel plates, right? This potential difference Q over C is all we used to figure out the capacitance. We didn't use the fact that it's parallel plate yet. So this is true for any capacitor. So that's the first piece of the lecture, the longer one, the energy stored in the capacitor. And I know there's beyond just the calc issues, not having learned about integrals yet. Is there anything, any other questions on the energy stored in a capacitor? Okay. So the other kind of common quantity or useful quantity is the energy density. All right, energy density here. We want to know, and the energy density is the energy per unit volume. All right, energy per unit volume. Because we can think of the energy in the capacitor as being stored in the electric field itself, right? When there's no charge on either plate of the capacitor, there's no electric field in between the plates, and there's no energy stored. The more charge you put on the plates, the bigger the electric field, the more energy gets stored in there. So we should be able to, and we should be able to come up with an expression for how much energy per unit volume there is in a parallel plate capacitor. Any ideas how we can figure this out? You have enough tools to kind of solve this now already.
Is it going to be the area times the distance between the capacitors, between the plates?
Well, what's going to be that? That's an important value.
That's the volume.
That's the volume, right? So yeah, let's start with that, right? And we got to be a little bit careful because voltage, potential, capital V, volume, also capital V. So I'll kind of be specific and write vol for volume. Yeah, volume is just the area times V, the distance between them, right? The area of the plates times the distance between them. So we definitely need to know that. What other information are we going to need?
The amount of energy that we have.
The amount of energy, right? So we're going to need one of these expressions that we just found. And we found 3 expressions, right? And the thing that we don't know is the charge, right? So we'll use the expression that we found that doesn't have the charge in it. The fact that the energy is just 1/2 capacitance times potential squared. Right, capacitance we're always going to know if we have a capacitor, and potential difference we'll be able to measure much, like I said before, more easily than the charge. So this looks good, and then I can almost get by, but I need one more. I'm going to need one more relation, right? What else am I going to need to know in order to figure out the energy per unit volume?
You're gonna have to need the charge, right?
We don't necessarily need the charge because we know the capacitance, and we'll say we know the capacitance and we know the potential difference. So if we need the charge, we can always figure it out from that. But what about we're going to, go ahead.
Well, what about the work then?
Well, this is the work, right? The energy in the capacitor is the work it takes to charge it. So we've got that. One more thing.
Well, then divide them then.
Okay, yeah, let's divide them and then see if we, yeah, okay, let's start with that. So energy density, and I'm trying to think of what's the AP test uses. I think it's just a lowercase u. So here's our energy density, which I'm using as a lowercase u now because I can't think of if there's a different symbol. But our energy density is our energy divided by volume, right? Which is 1/2 C times potential squared divided by the area and the distance. All right, so this would be my energy density, but there's a way that I need to simplify this. Because the area here and the distance here also shows up somewhere else in this. Yeah, the capacitance, right, depends on the area and the distance.
So could you factor, or unless you could change, like you could cancel out, right?
I could, but I mean, I don't have any of the same symbols here to cancel out. You're right, though. I do want to cancel out. What do I need to do if I want to cancel some stuff out?
You need to make sure you have like the same symbols or variables, right?
Yeah. So I want to make a substitution for one of these variables here, and I do have an equation that I can use to do that.
Well, C is equal to is equal to something over voltage.
Yeah. Well, right. C is equal to the charge over the voltage, right? So and if we plug that in, we'd be basically going back here and changing from this expression for energy to this expression for energy. But we still don't know the charge. But the way we can get some stuff to cancel out is if we remember we said this back at the beginning, but also in our last lecture, for a parallel plate capacitor, right, this is the capacitance for a parallel plate.
Q over V, yeah.
Right, which is the capacitance in terms of area and separation distance. So I can plug in this expression for capacitance into here. Right, this expression that says it's just that constant epsilon naught times A over D. So now when I plug this in here, I'll have I'll be able to cancel out A's and D's maybe. So I have 1/2 epsilon naught A over D times V times the potential squared, and then divided by A times D. So that's a second D, so that's a D squared. So the A's cancel out there, but the D's don't. So what I get is the energy density. Right, I'm going to label this energy density equals just epsilon naught times the potential squared over 2D squared, right, where D is the separation distance. All right, and I think that's all we need. I should let's see. Did anybody want to?
Did you move the 1/2 to the bottom?
The 1/2. Well, I moved the 2 to the bottom, right? Because 1/2 is yeah, it's the same thing.
Okay.
Yeah.
Okay. Cool.
Yeah. Any questions about what we've seen here today?
Nah, it looks pretty like once you like put everything together, it seems pretty straightforward.
Okay. Oh, all right. Yeah, there's a better.
Also, I searched it up. It's like it looks like an N or something like that.
Oh, yeah, I'm just looking right now for the symbol. It is no. This is the. If you look on, if we're on Survey and Jewett, we're looking at chapter. Hold on 1 second. Yeah, go. Yeah, if we're looking at chapter 7, where you're going for page 788. Sorry, chapter 26, page 788. They do have it is the lowercase u they're using for energy density there, and oh, they write okay. So yeah, it's we have got a good. So here's what we can do, because there's a better expression. When we came up with this, I was thinking this isn't the best way to write this for energy density. But we can make this even simpler if we want to write it in terms of the electric field, because we know that. Let's do it this way. Yeah, and the reason I want to do the energy density in terms of the electric field is because it's actually the expression we come up with is actually going to be true not just inside a capacitor, but it actually works for every electric field, right? If you have an electric field or a region of space where you know the electric field, this expression will give you the energy stored in that region of space, no matter what the electric field. Or the energy per unit volume at that point, no matter what the electric field is. So I'm going to use the expression that we know in between parallel plates anyway, which is where this comes from. We know that the potential is just the electric field times the distance between them, between the two plates. So what I want to do here is just plug in E times D in for my potential here. So I get my energy density is epsilon naught times ED squared over 2D squared, right? And now you can see, now I've got D squared and D squared, so my energy density is just 1/2 epsilon naught times the electric field squared. And that's a much simpler, much neater kind of expression. And it's also very useful because this is true for any point in space that has an electric field. The energy density of that point in space of that electric field is going to be 1/2 epsilon naught times E squared. And that becomes important later on when we look at electromagnetism. There's a very similar expression for the energy density of a magnetic field. That's 1/2 d squared, the magnetic field strength, with a slightly different constant. So that's where we were looking to get to with the energy density. We found the energy density. We derived it for the energy for inside the electric field inside of parallel plates. And I'm not going to derive this in general. I'm not sure if Sirway and Jewett even do in the textbook, but at least until you get to higher level physics courses, you'll just take my word that it's true. This expression is true not just inside a capacitor, but basically anywhere where there's an electric field. Okay. Questions, comments? All right. Well, I'll stop the video
So
there.
this is only for parallel plates.
This is for parallel plates, right? And then when I went back and replaced the potential between a parallel plate with what we know the potential between parallel plates is, which is E times D, what I ended up with is this expression, which is the energy density for any electric field.
Oh, okay.
I'm sorry, it was a little confusing about how general this is. This is for any electric field. This is only parallel plate capacitors. Okay.